if it ends up in this hole,
So
then it's gone, right? If it ends up in this hole, it's gone.
bigger than 727.
Bigger than
Or
727.
smaller than 2727.
Smaller than
7
727.
is 0.259. 259.
Okay.
259.
We could also get a common denominator and entertain ourselves with the numbers again, but. So what's a quarter do as we follow it through here? It's in the bottom third, then it's in the top of that third, then it's in the bottom of that third. Next time it'll be in the top of that third, flips back and forth. Never goes away, just switches which third it's in. Something to think about later. A little awkward, but quarter goes back and forth between the bottom and top thirds of the interval it was last in. So it is in the Cantor set. It's still there when we get done. Okay? And there, in fact, are lots of such numbers that are there when we're done. What's that mean?
3/4.
3/4. 3/4 ought to be there. Same rule, same reasoning as a quarter, right? So. The Cantor set is very odd. Our typical models that we think about in our normal life are the real numbers, which are nice and continuous and thick. There's lots of them there, right? And then the integers, or maybe the rational numbers, which are sort of separated, right? The Cantor set is somehow in the middle of those two ideas. And what does that mean? So the Cantor set was, actually this model of the Cantor set is called the Cantor ternary set for the middle third. Okay, you could do this with cutting out the middle quarter, or you could do it with cutting out a quarter on each side, or you could cut out whatever interval you want, right? As long as it's an open interval so that you're clearly leaving those endpoints. There are fascinating extensions of this idea. Cantor actually, George Cantor, who lived from 1845 to 1918, I wrote that down because I knew I'd forget it, actually was not that interested in the ternary set. It is the one that is most typically introduced as a starting point. His interest was more in that general idea of removing open things and what's left. Okay, so open means not including the endpoints. Everybody good? All right. So it turns out that this, somewhere in the middle of the real numbers that we're accustomed to and the integers, for example, of things that are very easily, clearly separated, the Cantor set is the foundation for most modern topology. It is considered one of the easiest fractals to get your hands on, right? It's not quite as pretty as maybe the Mandelbrot set, but it still has that self-similarity of, if I look at this piece and magnify it, it looks just like the whole here. So it is a fractal, and is a really nice elementary example when you're trying to prove things about fractals or explore them. It's very fewer things to think about, right? So that's nice when you're trying to find an example or a counterexample to something, because you don't get as distracted by maybe those other things to think about. All right, so let's think about what is the length of this set. I lost the chalk. There we go. What is how long is T infinity?
Wow.
0.
Huh.
Those are two answers I heard so far.
Really small.
By long, using the length of each piece.
Yeah, what do we mean by long?
Something that you measure with the ruler.
Okay, typically something we measure with a ruler. Or-
Does it include the spaces?
Yeah, should we include those spaces? Because those spaces aren't part of T infinity, right? T infinity is what's left after we take out all those spaces.
Zero.
So yeah, it's like, how much of this is left? Right, how long is all those little left pieces? Does that make sense? So if one of those was just a little bit in distance, right, then we could add all those up, and we'd have the length.
So does that mean that T1 is 2/3?
Yes. So that's what we want to do next. So let's go back and think about the length. The length of T1 is 2/3, right? 1/3 here, 1/3 there makes 2/3. Length of T0 was 1. Length of T2,
1 9.
Times 4.
4.
4 ninths.
Yeah.
Does everybody agree? 1 ninth times 4. More conveniently known as, even better as, why? Because it's 2/3 right there of the 2/3 that we had over there. 2/3 of 2/3. I don't know where to write that. Of means multiply, so we get 2/3 times 2/3. So what's the length of T3? 2/3 of 2/3 of 2/3. So what's the length of Tn? Because that's easier to think about than T infinity.
2/3 and
2/3 to the n. Pretty good. And we do this for how long? Forever. Right? So the length of the Cantor set is the limit of the lengths of the T sub n's as n gets really big. Right? That's what it means to talk about a T infinity, is let n go to infinity. But I know what that length is. The length of T sub n is 2/3 to the n. So if I multiply 2/3 times 2/3 times 2/3 times 2/3 times 2/3 forever, I get I'll say it again. So if I multiply the 2/3 times 2/3 times 2/3 times 2/3 times 2/3 times 2/3 forever, I get 0. Wait.
no, you
How could that be? Yeah, I get really, really small, right? So 2/3 times 2/3 is little. Times 2/3 is
even smaller.
even littler. And if I let that happen forever, it eventually goes to 0. How long is the Cantor set? It has measure 0. It has stuff. Right, we said that first. Yes, there's stuff, but it has no length. Well, that's weird.
Weird.
That is the whole point of today. Oh, well, that's weird. Okay. You're doing good.